Okay, our next speaker is Samson Zhou for talk about fast and space optimal streaming algorithms for Euclidean plastic.
All right, yeah, thanks for the introduction, and thanks for the organizers for putting together this wonderful program. Yeah, so this is joint work with Vincent Cohen-Dadad, who's at Google, David Woodruff, who's at Carnegie Mellon, Liudeng Wang, who'll be starting at A&M in 2 days. We'll get a picture of him soon. And yeah. All right, so the one-slide summary of what I'm going to talk about is we'll have a stream of data points, and our goal is just to quickly cluster a stream of endpoints using O of one space. Right. So there are some caveats here. I'll go into that, but this should be the overarching goal. All right. So in K clustering, we're given input data set X, and we want to find a set C of K centers that implicitly partition the data set X into K different clusters while minimizing some associated cost function of clustering. So if this is our data set, and we say that we want to group it into K different clusters for K equals 3, then the natural partitioning would be this group of points here. OK, so in this talk, we'll focus on KZ clustering. And so the cost of a set C on the data set X is going to be the sum of the zth powers for each point to its closest center. Okay. So here we have a slide that has K equals 1 center, and these are the points. So the K median clustering cost is where Z equals 1. It's the sum of the distances from each point to the center. K means is where Z equals 2. In general, we'll look at KZ clustering. Okay, and in this talk, we'll also focus on Euclidean K clustering. So the input points will live on a grid. So they'll all be integers. You can think of this just as like, the number of bits in the representation of each coordinate. So the aspect ratio will be 1 to delta, and we'll have d coordinates. Okay. And so then the distance between 2 points is the standard Euclidean distance. All right, so this is a streaming model talk. So we'll have an underlying data set X that arrives sequentially. And in the case that we consider, at each time t, we want to output a good set CT of K centers. Again, we can't actually give each point its closest label, because if they're endpoints, that would take n space. So again, we're doing implicit clustering. And our first goal is to use space that's sublinear in the size n of the input. In fact, we want space completely independent of the input. And we want fast update time for some definition of fast. Okay. So actually, we get something stronger. We get a core set. And what a core set is a weighted subset X prime of the represented points of X for a specific clustering objective, K means, K median, whatever. So let's suppose that these are all our input points. Then we might choose a subset of these 4 red points, weight them, and then for any choice of K centers, the cost of clustering these red weighted points should be roughly the cost of clustering the original data set. Okay, and it's actually known that for KZ clustering, there exists core set constructions that require some number of weighted points that's independent of n. Okay, so there's a long line of work. I guess the rule of thumb is that C is Vincent Cohen-Dadad. If there's one S, it's Chris Schwiegelson. If there are 2 S's, it's David Salpick. Okay. So the main takeaway here is that the size of these core sets is independent of the size n of the input. Right? So that should be our corresponding goal for the streaming case. Okay. All right, so goal number 1, we want to cluster a stream of endpoints using space that's independent of n. And our goal 2 is actually to cluster using O of k, little o of k, amortized update time. So the way to think about this is that each time we get an update, we don't want to recluster the entire set of points. Okay, so our first result is that there exists a one-pass algorithm on insertion-only streams that maintains a 1 plus epsilon core set at all times in the stream, and indeed uses words of space that's independent of n, In fact, this quantity right here matches the offline optimal constructions in the earlier slide. And we get amortized update time little of k. Okay. And as a corollary, if you actually want a good set of centers, we can't get a 1 plus epsilon approximation. There are hardness results known for this. It's APX hard. But we can get a constant factor approximation. And so we can do this again using the same amount of space and same amount of amortized update time. Okay. So the difference between these two results is this one is giving you a 1 plus epsilon core set. One is giving you actually k centers. That gives a good clustering cost. Okay, so to give some context, there's been a line of results that start off with some exponential dependency in the dimension. This is an epsilon network. Then there's a lot of number of works that have some kind of dependency log n. Recently, we took this down from log n to poly log n, and finally we said, all right, we can just match the offline construction. So there's no price for working the streaming model. So that's space. Now for update time, there's been less work done on this. But the previous works all maintain some kind of core set. And they get amortized update time either k squared or k, some polynomial dependency in k. Now, I should say that these results are not really comparable to ours. I mean, ours looks better because we have a log k instead of a k, and then polylog n instead of polylog n. But these works work in the fully dynamic setting where you can add and delete points. And we really require the fact that our stream is incremental, so we can only add points. OK. So this, I guess, is a graph sparsification workshop. So I should talk about graph sparsification. One other application of our techniques is the subspace embeddings. So in this problem, we have a matrix A. It's n by d. So what happens is just that the n rows arrive one at a time. It's analogous to clustering because you can imagine your n points in d-dimensional space arrive one at a time. So the rows that arrive define a matrix A. And the goal is at every time, find a matrix M with a much smaller number of rows, such that for any vector x, the 2 norm of ax is roughly the 2 norm of mx. Okay, this needs to hold for all vectors x. OK, and it's known that this is a stronger guarantee. This is a spectral sparsification. So it can be used to approximate all cuts of a graph when the rows of A correspond to graph edges. That being said, we don't solve the graph sparsification problem. Our results are not optimal there, so that'll be an open problem at the end that I want to find a solution to. OK, so for subspace embeddings, we also get a space bound that's independent of the number of rows. OK, this is bits of space. Sorry, this should say bits of space, not words of space. And the amortized update time is just basically the amount of time it takes to read a row. OK, we also have some results, some structural properties that we call efficient encodings. And they give improved communication bounds for clustering distributed models. I'll talk about that next week at WOLA. OK, so yeah, maybe I'll stop for questions. Otherwise, I'll start talking about the constant space algorithm. Any questions?
Space, it has dependence on k, right?
Yeah. So this is omitting dependencies on k, d, and epsilon. It's just constant in terms of n. So in terms of the actual space, we'll basically be keeping k over epsilon for k means. We'll be keeping like k over epsilon to the 4th words or points. So each one will have dimension d, and then we'll actually store some of the coordinates.
So if your space doesn't depend on n, and the new point that comes in doesn't depend on n, how can the update time depend on n?
Oh, because it's words of space. So like we do some bit tricks. Yeah, exactly. OK, so yeah, if there are no questions, we'll talk about how to get a constant space algorithm in terms of n. This algorithm is really simple, so it's my hope that everyone will understand this algorithm. Maybe the second goal, I won't be so ambitious. Okay. So before we talk about our algorithm, we'll talk about a classic algorithm in the stream model. So this is something that's been done for a long time. It's very simple. It's just merge and reduce. Okay. So if you have some core set construction, let's say for k-means clustering, and it uses a certain number of weighted points. So you have your data set, and it's known that there is a core set for k-means clustering that just uses roughly k over epsilon to the 4th points. Then what you can do is you can take your stream, this is the bottom, you can break it up into blocks or chunks, I forget if I, anyway, blocks, and you can create a core set for each block. And then you can use a binary tree. So when you have 2 core sets for adjacent blocks, you can just make a core set for these 2 core sets. Okay. Now the issue is that you will incur some amount of distortion each time you make a core set of core sets. And so if you want 1 plus epsilon approximation at the top, at the root of the tree, which represents the entire stream, well, the height of the tree would be like log n. And so you need roughly 1 plus epsilon over log n approximation for each of these core sets. And that means that the number of points that you'll be keeping is roughly k over epsilon to the 4th times log cubed n. Okay. You pay a little for your approximation. You pay 2 log n factors for your approximation, and then you pay another log n factor for how many core sets you need to maintain for the height of the tree. All right, so the key point is this is not independent of the size n of the stream length. But it'll give us some insight on what to do next. Okay, so this is merge and reduce. Another approach that is common is called sensitivity sampling. And this is basically importance sampling. So if we have a data set x, what we can do is sample some number of points of x based on how important each point looks. So if we look at the, this point on the right, it looks quite different than the other points. In fact, if we have 3 centers that kind of sit at the middle of each of these 3 clusters, then most of the cost will be induced by this point on the right. So this point looks important, and that means that the sensitivity of this point should be pretty high. Okay. Again, it's just a measure of how important each point is. Now, the challenge is that we can't actually compute the sensitivity of each point because that requires seeing the entire data set x, but then it's too late to sample the point. But we can define a similar notion called the online sensitivity of a point, which is just how important a point looks compared to the points that have arrived so far, the prefix of the stream that it can see. So this is an upper bound on the actual sensitivity. And so we can actually use our core set so far to get a good approximation to this online sensitivity. And then we can sample the point with probability proportional to its importance. OK, so there's some math to be done. But the point is that if we do this, we can get a core set that samples roughly k squared d over epsilon squared times polylog n delta points. Right? So this is just an alternative way to get a core set for a stream. It still has polylog n factors, so it doesn't get to our goal. All right, but it's another way of doing it, and it's pretty simple. And the key part is online sensitivity sampling is it's kind of committal. So once you sample a point, you'll always keep it. And so you can view the points that you sample as a new stream x prime. Okay? You see x, it's n points. As it goes on, you sample some of these points. The points that you sample will be new insertion-only stream x prime. And now you can do this algorithm that we did previously, where you perform online sensitivity sampling to create a new stream x prime, and then you just run merge and reduce on x prime. Now, what's the point of this? The point of this is that merge and reduce previously incurred a logarithmic dependency on the length of the stream because of the binary tree. And now the length of our stream, x prime, is much shorter, right? Because it's like k squared d over epsilon squared due to the sensitivity sampling. And so the total number of points now is going to be k over epsilon to the 4th times polylog length of the new stream x prime. Okay. So that means that the dependency has now gone down from log n, polylog n, to like polylog log n. So we're not there yet, but we've, I guess, technically gotten exponential improvement. OK. So to be more specific, the number of points is like k over epsilon to the fourth times polylog log n. And there are actually polylog log n groups of this number of points, where each group corresponds to one of the core sets. Okay. So the point is now that if we want independence of the size n of the stream length, we can't afford to store all points explicitly, because the number of points is too large. So pictorially, this is what it looks like. We have a stream x. We do online sensitivity sampling to get this shorter stream length x prime. And we have L groups, where each of the groups corresponds to one of these core sets. OK. But again, we can't afford to store each point explicitly. So instead, what we'll do is this efficient local encoding, where we look at a specific group, gi, and we compute a near optimal solution, si. So just think of some constant factor approximation. OK, so now we're going to encode each point by storing the offset of each point from one of the centers of this constant factor approximation. So you take your point in this group, and you let Cx be the closest center in this constant factor approximation to the point. And so the offset is this difference right here. Okay, so basically x is equal to I guess the center minus y. And now we're going to round each coordinate of y to the nearest power of 1 plus epsilon prime for some epsilon prime that I'll tell you about. And we're going to store the exponents of these coordinates. So it's a better encoding. Right, so this is what it looks like. Let's suppose that we have this point x. These triangles are a constant factor approximation. And so this right here is the offset. Right, y is cx minus x. And now we're going to round the coordinates of y. So it won't be like this anymore. It might be, we might overshoot a bit. Okay. But the key part now is that we don't have to store the coordinates of y tilde explicitly. We can just store the exponents. And so if we set epsilon prime to be poly epsilon over log n d delta, then each point will use a log number of this amount in bits. And so each group will use the right number of words of space. So we're almost there. Right? We have good encoding for each group. But the bad part is that we still have a large number of groups. Okay, so the TLDR is that by this efficient encoding, we still get a good core set for each core set. Right, so this rounding trick will be a better way to represent each of these core sets. But again, the problem is that we still have too many of these groups. So our last step is to use a global encoding instead of a local encoding. And that just means that instead of storing a constant factor approximation for each group, we'll store a global constant factor approximation. Okay, so we don't have the same number of groups anymore. We don't have like a polylog number of constant factor approximations. And now we store the offset of each point from one of the centers of this global constant factor approximation. You lose the property that these roundings are going to be a 1 plus epsilon approximation for each group. Okay, so the rounded points no longer provide a 1 plus epsilon approximation for each group, but it gives additive approximation error with respect to the global constant factor approximation, which is all that you need. So this global rounding gives a slightly weaker property than before. We don't preserve each of these core sets anymore. But the important thing is that we still preserve the core set at the top. Right? So yeah, the algorithm is quite simple. It's just we're performing some sampling to implicitly create a new stream x prime. We're going to run merge and reduce on x prime, and then we're going to do a better global encoding on the resulting core sets from this merge and reduce. That's the whole algorithm for the constant space approximation. So yeah, maybe I'll stop for questions. Otherwise, I'll go. If there are no questions, I'll go into fast update time.
It only works for insertion only a strings. So each part is the bottleneck, is the online sensitivity sampling that doesn't work in the dynamic.
Yeah. So yeah, the bottleneck is online sensitivity sampling. The point is, if you sample a point for online sensitivity sampling, we'll always keep it. But in insertion deletion streams, we might delete these points, right?
But the other thing is
merge and reduce also doesn't actually work for insertion only or for insertion deletion streams.
you said there was some prior work that also worked in dynamic stream.
Oh yeah, so for dynamic streams, they don't actually have in their setting they don't have sublinear space, so they actually keep the entire set of points. Okay, so if there are no questions, I'll go fast over this, which is appropriate because yeah, our algorithm needs to be fast. So the bottleneck, as Ali mentioned, is that the runtime bottleneck is that we actually need some way to approximate how important each point looks. And this is kind of a chicken-egg problem because like computing a good approximation to how important each point looks often actually involves solving like an approximately optimal clustering problem. And clustering is difficult. There's an algorithm by Gupta and his student that says that constant factor approximation can be done in time dn squared, where n is the input size. So the good thing is that we can view n as our core set size. So n is quite small, but it's still quadratic. It's not good. Okay, like if we did this naively, we would get like a k squared update time. Okay, so yeah, our previous algorithm utilized a significantly smaller stream, right? We sampled points, and then we said, all right, now that we have a small number of points in the stream, we can run merge and reduce on this. So we can actually do this again. Namely, let's create a stream x tilde with roughly length something that's sublinear in n, just tiny bit sublinear in n. And then we can essentially be really slow on each update to the stream, right? Okay, so how do we create the stream? Well, again, we can use online sensitivity sampling, but the gain is that now we just need really crude approximations to the importance of each point. Okay, so before I said that if we want a good approximation to how important each point is, this is approximately solving a constant factor approximation clustering problem, and that's slow. But you can imagine if we want crude approximations, we can do a lot better. Okay. So yeah, our main structural result is that there exists some algorithm that will give you crude approximations to how important each point is for a batch of k points using time that's sublinear in, logarithmic in k and log n delta, right? So this combined with everything else I said before should give you an end-to-end algorithm for how to do this. You use these quantities to create a stream like x tilde, and then on x tilde, you just run some much slower algorithm per update. Okay. So how do we do this? We show a number of structural properties. First, we show that clustering costs and importances of points are only disturbed by a constant factor when we constrain the centers of the clusters to being points of the input set. This is known as the k-supplier problem or k-meteoroids. And once we choose a center for each point, then looking at the sensitivity or the importance of a point is an optimization problem. Once we fix a center C that serves this point, then we just want to minimize the clustering cost. Okay. And the good part is now that we constrain our cluster centers to being among the centers in the data set, that means that brute force enumeration is much faster because we only have a small number of points, like k over epsilon to the fourth again. Okay, so we can actually enumerate over all the centers. Okay, so we want to solve this constrained optimization problem by saying that, well, we're going to guess a center C that achieves the maximum importance for this point x. And now we want to minimize the actual clustering cost of a set big C whose closest center to the point is our guess. So the way we do this is with a standard quad-tree embedding. So if you haven't seen this before, we just throw all the points in a grid. Then we cut this grid in half, then in fourth, so on and so forth. And then if we have a set of centers with some amount of capacity, the clustering cost induced by this quad-tree is going to be, well, here, all the centers are in the same grid, in the same cells as the points. Maybe at this lower level, this center right here is not in the same cell as these 7 points. And so the contribution of this level to the clustering cost is like delta over 2 times 7. And this repeats so on and so forth. OK, so the way I said this, the grid is split in half. But more generally, or for our purposes, we'll choose the side lengths of the grid L to be zeta to the L, where zeta is actually much bigger than 2. It's like n to the 1 minus c, which means that we only need like a constant number of levels in this quad-tree. Okay, so there are like only a small number of grids. And that means that we can do nearest neighbor search much faster because there's only the small number of grids that can go up and down. And that implies that we can quickly solve a near optimal clustering problem. And we also use some additional structure to quickly approximate the constrained clustering problem. So maybe in the interest of time, I'll skip past these properties. Yeah, and I'll briefly stop for questions. Otherwise, I'll go into subspace embeddings. All right, so yeah, this is basically the framework we talked about before. We had importances for each point, and we're going to replace the importances for each point with the importances of each row. So the analog of sensitivity sampling for points for clustering is leverage scores for matrices. So we're going to sample each point, each row, by its online leverage score. This will create a new matrix A prime that has a much smaller number of rows compared to the original matrix. Again, we run merge and reduce on A prime. And then we use some kind of efficient global encoding on the core sets from merge and reduce. Okay. So I'll talk briefly about the encoding. It's a bit different because previously we took the offset of each point to its closest center. And now this doesn't make sense for matrices anymore. So what we do for each row is that we multiply the row by a deterministic preconditioner, where the preconditioner is going to give you a constant factor subspace embedding. And then we round each coordinate in the resulting multiplied row. Okay. OK, so that is going to give a good space bound. And then for fast computation, we again need a crude approximation to how important each row or point is. It's known that if we have a constant factor subspace embedding M to the matrix A, then we can compute, there's an explicit form to how important a row is. Okay. In fact, if we take a random Gaussian, then we can get a good approximation of how important this row is. And this can be done quickly. Okay. So the summary, again, is that there are these analogs to clustering. There's importance, there's merge and reduce, and then there's good efficient local or global encoding. Okay. Yeah, so putting things together, in summary, we get 1 plus epsilon core sets for clustering and subspace embeddings. Our algorithms use words of space independent of the stream length and fast amortized update time. And this is kind of a general framework, but there are other problems that fit this framework that we haven't been able to solve yet. So the main problem that comes up to mind is low rank approximation. So we haven't been able to find a efficient local encoding for low rank approximation yet. There probably exists one, but everything else goes through. There's a good sampling scheme. You can run merge and reduce. You just need a good way to encode the actual rows. And maybe the most relevant question to all of us, and a question that, it'd be great if someone could find the answer to, is whether you can do this for graph sparsification. So the key point for graph sparsification, or the gap, is that when we have each row, we're able to round the coordinates of a row. But now, when the rows correspond to edges, they're just the 2 vertices. that are the endpoints of the edge. And it doesn't make sense to round those things. So it's unclear whether there is a price to pay for graph sparsification in the stream model. It'd be great if one of you could solve the problem. Okay, that's all I have. Thanks for your attention.
Okay, not let's thank the speaker again. The next talk is at 4.